Hello, in this lecture we'll answer two questions. In the first question, we find out the area of this great shape using two different methods. And in the second question, we find out the radius of this semicircle that is described by rectangle ABCD. So we'll start with the first question. In the drawing, we have rectangle ABCD. This is line segment AE, this is equals to 1 unit in its length. Line segment side AB equals to 3 units in its length. And inside this rectangle, we have this green shape. The green shape is actually the green triangle BEC. The green shape is a triangle. So our task is to find out the area of this triangle BEC. In addition, we know that this is angle BEC. This is equals to 45 degrees in its size. Again, our task is to find out the area of this triangle BEC. That is the green shape. So first of all, ABCD is a rectangle, therefore all those four angles are right angles. In the next step, we will define the length of this line segment ED as x. We also know that the opposite sides of rectangle are equal to each other. So in rectangle ABCD, side AB equals to the opposite side DC. But AB is 3, therefore the opposite side DC must be also equal to 3 units in its length. Likewise, according to the sum rule, in the same rectangle ABCD, side AD must be equal to the opposite side BC, but AD in total is 1 plus x, therefore the opposite side BC must be also equal to 1 plus x units in its length. In the next step, we will do a construction. That is also from point E, this point E, we will go perpendicular on BC. So actually, this angle equals to 90 degrees inside, and this angle also equals to 90 degrees inside according to our construction. We define the touching point of the perpendicular from point E and BC. This point is point M. By doing this construction, before that we define the length of the perpendicular EM as h. It is information for the height. H is the height to the base BC of the green triangle EBC. So it is information for height. So by doing this construction, we create quadrilateral ABME. Inside quadrilateral ABME, we have 1, 2, 3 rectangles. The sum of 3 rectangles is equal to 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that said that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So in the small upper quadrilateral ABME we have 4 rectangles. Therefore quadrilateral ABME is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in the small upper rectangle ABME, side AB must be equal to the opposite side EM. But AB is 3, therefore the opposite side EM must be also equal to 3 units in its length. EM equals to H and H equals to 3. That is to say, the height to the base BC of the rectangle BC equals to H and H equals to 3. In the next step, we will implement the Pythagoras theorem on this right upper triangle, triangle ABE. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is a version for Pythagoras theorem. So in this right upper triangle ABE, according to the Pythagoras theorem, BE squared, that is the square of the hypotenuse, equals to AB squared plus AE squared. Repeat again, in this upper right triangle AEB, according to the Pythagoras theorem, BE squared, that is the square of the hypotenuse, equals to AB squared plus AE squared. BE is the missing hypotenuse, so limit as it is, so it is BE squared equals to AB squared. AB is 3, therefore AB squared is 3 squared, that is 9, plus AE squared. AE is 1, therefore A squared is 1 squared, that is 1. So total we found out that BE squared equals to 9 plus 1, that is 10. BE squared equals to 10. Here we take a root out of this equation and find out that the missing hypotenuse BE is equal to the square root of 10 units in its length. This is the hypotenuse BE that is equal to the square root of 10 units in its length. In the next step, we will implement the Pythagoras theorem on this right lower triangle, triangle EDC. Here by PT is a version for Pythagoras theorem. This right lower triangle, triangle EDC, according to the Pythagoras theorem, EC squared, that is the square of the hypotenuse, equals to ED squared plus DC squared. So write it down. EC squared equals to ED squared plus DC squared. Repeat again, in this right lower triangle EDC, according to the Pythagoras theorem, EC squared, that is the square of the hypotenuse, equals to ED squared plus DC squared. EC is the missing hypotenuse, so we limit as it is, so it is EC squared equals to ED squared. EC squared is the missing hypotenuse, so we limit as it is, so it is EC squared equals to ED squared. ED is x, therefore ED squared is x squared plus DC squared. DC is 3, therefore DC squared is 3 squared, this is 9. So today we found out that EC square equals to x square plus 9. Here we will take a root out of this equation, and we will get that the missing hypotenuse EC on the right lower triangle EDC is equal to the square root of x square plus 9 units in its length. So it is known. This is the missing hypotenuse EC. This is equal to the square root of x square plus 9 units in its length. Our task is to find out the area of this green shape. The green shape is actually a triangle. So our task, triangle EBC. So our task is to find out the area of this green triangle, triangle EBC. Therefore, we calculate the area of this green triangle EBC by using two different methods. And then we will create equation 3 that says that the area of this green triangle according to the first method of calculation must be equal to the area of this green triangle EBC according to the second method of calculation. So in the first method of calculation, the area of this green triangle EBC, now that the area of any triangle equals to the base of the triangle times the height over 2. We choose the base of this green triangle EBC as BC, so it is the base BC times the height edge. The height edge is edge because it's greater than 90 degrees with the base BC. So the height is edge. This is equals to 3 over 2. So in total we should find out that according to the first method of calculation, the area of this green triangle EBC is equal to the base BC times the height edge over 2. The base BC equals to x plus 1 units in its length times the height edge, that is 3 over 2. So in total we actually found out that the area of this green triangle EBC according to the first method of calculation equals to x plus 1 times 3 over 2. The area of the green triangle EBC according to the first method of calculation is equal to 3 times x plus 1 over 2. In the next step, we calculate the area of this green triangle in a different way. This is triangle ABC that could be any triangle. Repeat again. This is triangle ABC that could be any triangle. The length of side AB is equals to A units, side AC equals to B units in its length, and the angle between those two sides is theta. The area of this triangle, triangle ABC that could be any triangle, equals to the multiplication of those two sides by each other, this is to say A times B, times the angle between those two sides, that is theta over 2. Repeat again, the area of this triangle ABC equals to A times B times theta over 2. So we use the new formula in order to find out the area of our great triangle, triangle EBC. So the area of the great triangle EBC according to the new formula that I presented to you will be equal to EB times EC times sinus 45 degrees over 2. And again, the area of this green triangle EBC will be equal to the multiplication of those two sides by each other. That is to say, it is EB times EC. Times sinus diagonal between those two sides, that is 45 degrees, so it is sinus 45 degrees over 2. So in total, we found out that the area of this green triangle EBC according to the second method of calculation is equal to EB times AC, that is the multiplication of the two sides of the triangle by each other, times sinus diagonal between the angle, times sinus diagonal between the two sides, that is 45 degrees over 2. Repeat again, the area of triangle EBC according to the second method of calculation equals to EB times AC times sinus 45 degrees over 2. And we already found out that according to the first method of calculation, the area of this green triangle EBC is equal to 3 times x plus 1 x plus 1 over 2. Again, repeat again. The area of this green triangle EBC according to the first method of calculation equals to 3 times x plus 1 over 2. So in the next step, we create the equation 3 that says that the area of the green triangle EBC according to the first method of calculation must be equal to the area of the same green triangle EBC according to the second method of calculation. So it is known. Question 3 states that the area of the green triangle EBC according to the first method of calculation must be equal to the area of the same green triangle EBC according to the second method of calculation. And we already found out that the area of the green triangle EBC according to the first method of calculation equals to 3 times x plus 1 over 2. And it must be equal to the area of the same green triangle EBC according to the second method of calculation, that is equals to EB times EC times sinus 45 degrees over 2. Very simple equation. Okay. So according to equation 3, 3 times x plus 1 over 2 equals to EB times EC times sinus 45 degrees over 2. We already found out that the length of side EB is square root of 10. Times EC. The length of side EC is equal to the square root of x squared plus 9. Times sinus 45 degrees. Sinus 45 degrees equals to the square root of 2 over 2. And we have to divide all by 2. We have to divide it by 2. We have 2 on both sides of this equation 3, so 2 will get cancelled. And we left with these 2 on the side of the equation. So in total, after we cancel 2, according to equation 3, we get that 3 times x plus 1 equals to the square root of 10 times the square root of 2 is the square root of 20. Here also times the square root of x squared plus 9 divided by 2. So according to equation 3, we actually found out that 3 times x plus 1 equals, we substitute 20 inside the root by 4 times 5. So we substitute 20 by 4 times 5. Times the square root of x squared plus 9 over 2. So according to equation 3, 3 times x plus 1 equals, the square root of 4 is 2, so we take 4 out of the root, so inside the root we left only with 5. So it is 2 times square root of 5 times x squared plus 9 over 2. So here we have 2 in the numerator, 2 in the denominator, so 2 will get cancelled. After cancelled 2, we should find out in total that according to equation 3, 3 times x plus 1 equals to the square root of 5 times the square root of x squared plus 9. And again, in total, after cancel 2, we found out that according to equation 3, 3 times x plus 1 equals to the square root of 5 times the square root of x squared plus 9. So here we will square both sides of this equation 3. So in this side of equation 3 we have 3 squared, that is 9, and we have to square also x plus 1, so it is x plus 1 squared. So in total, after we square this, the equation, both sides of equation 3 by, we square both sides of the equation 3. In this side of equation 3 we have 9 times x plus 1 squared. While on the other side of this equation 3 we have square root of 5 squared, this is 5, and the square root of x squared plus 9 squared equals to x squared plus 9. Why? Because of the fact that the square cancels the root, we are left only with x squared plus 9. So in this side of the equation we are left with 5 times x squared plus 9. Here we will open the brackets on both sides of this equation 3. And get that according to this equation 3, we have 9 times x plus 1 squared. X plus 1 squared equals to x squared plus 1 squared, that is 1, plus 2 times x times 1, that is 2x, and this equals to 5 times x squared is 5x squared, and 5 times 9 is 45. So here we will open the brackets on this side of this equation 3, and we get that according to equation 3, 9 times x squared is 9x squared, plus 9 times 1 is 9, plus 9 times 2x is 18x, and this equals to 5x squared plus 45. Here we subtract 5x squared from this equation 3. So 9x squared minus 5x squared is 4x squared plus 9 plus 18x. So 5x squared minus 5x squared is 0, so we left only with 45 on this side of the equation. Here we will subtract 45 from this equation 3. And find that according to this equation 3, 4x squared plus 18x, and 9 minus 45 is minus 36, equals to 0. Here we will divide this equation 3 by 4. And again, that according to this equation 3, we have 4x squared over 4 is x squared, plus 18x over 4 is 4.5x, and minus 36 over 4 is minus 9, equals to 0 over 4 is 0. So in total, we found out that x squared plus 4.5x minus 9 equals to 0. So this is the quadratic equation. And the general formula for a quadratic equation is as follows: ax squared plus bx plus c equals to 0. In this general formula of a quadratic equation, a, b, and c are the coefficients of this quadratic equation. x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, that is to say x squared plus 4.5x minus 9 equals to 0, in our quadratic equation, the variable that we're looking for is x. X is the length of line segment ED. Write it down. X is the length of line segment ED. The coefficient A equals to 1. The coefficient B equals to 4.5. And finally the coefficient C equals to minus 9. And the general formula for x is as follows. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. So the only thing that is left to do in order to find out the value of x, that is the length of line segment ED, is just to put the data of our specific quadratic equation inside this general formula for x. In this way, we find out the value of the values of x, because x might have two solutions. So we do it now, and we get that x equals to minus b. B is 4.5, therefore minus b is minus 4.5 plus minus square root of b squared. B is 4.5, and therefore b squared is 4.5 squared. This is 20.25 minus 4 times a times c. So it is minus 4 times a. A is also minus 4 times 1 is minus 4 times c. C is minus 9, and minus 4 times minus 9 is plus 36 over 2a. A is 1, so 2a is 2 times 1, this is 2. So in total we found out that x equals to minus 4.5 plus minus, inside the root we have 20.25 plus 36 is 56.25. Divided by 2. So in total we found out that x, that is the length of this line segment EO, the length of this line segment AD, is equal to minus 4.5 plus minus the square root of 56.25 is 7.5 over 2. So here we have two solutions that are possible for x. The first solution for x is as follows. X equals to minus 4.5 minus 7.5 over 2. Minus 4.5 minus 7.5 is minus 12 over 2 is minus 6. So we found out that x equals to minus 6. But it is impossible that x equals to minus 6 because x is the length of this line segment AD, so x as a length, it must be a positive number. Minus 6 is a negative number, so the first solution for x is an incorrect solution. You can set the solution, and we will take into account only the second solution for x. The second solution for x is as follows. X equals to minus 4.5 plus 7.5 over 2. Minus 4.5 plus 7.5 is 3 over 2 is 1.5 units in its length. So if you found out that x equals to 1.5 units in its length, that is to say, this is 170 indeed equals to x and it is equals to 1.5 units in its length. Our task is to find out the area of this green shape, that is actually the area of the green triangle ABC. The green shape is actually the green right triangle ABC. So our task is actually to find out the area of the green right triangle ABC. Note that the area of any triangle equals to the base of the triangle times the height over 2. And therefore, we'll choose the base of this green triangle BEC as BC. So the base is BC times the height. The height is h because it's less than 90 degrees with the base BC. So the height is h over 2. So in total, the area of the green shape equals to the base BC times the height h over 2. We only found out that BC equals to 1 plus x plus 1. So BC equals to x plus 1 times the height h is 3 over 2. X is 1.5 and therefore x plus 1 is 1.5 plus 1, that is 2.5. So the base BC equals to 2.5 times the height h, that is 3 over 2. .5 times 3 is 7.5 and 7.5 over 2 is equal to 3.75 square units in its size. Repeat again, if you found out that the area that we are looking for this question, that is the area of this green shape equals to 3.75 square units in its size. So we finish with the first method. In the next step I present to you how to find out the area of this green shape according to the second method. ABCD is a rectangle, therefore all those four angles are right angles. We define the length of this 170 ED as x, exactly as we did in the first method. We also know that the opposite sides of rectangle are equal to each other. So in this rectangle ABCD, side AB equals to the opposite side DC. But AB is 3, therefore the opposite side DC must be also equal to 3 units in its length. Likewise, according to the same rule, in the same rectangle ABCD, side AD must be equal to the opposite side BC, but AD in totality is x plus 1, therefore the opposite side BC must be also equal to x plus 1 units in its length. In the next step, we will do a construction, exactly as we did in the first method. That is to say, from point E, we will draw perpendicular on BC. And again, from point E, we will draw perpendicular on side BC of rectangle ABCD. So actually, this angle equals to 90 degrees in its size, and this angle also equals to 90 degrees in its size according to our construction. We will define the touching point of the perpendicular from point E and BC. This point is point M. When doing this construction, we created the small upper quadrilateral ABME. Inside this quadrilateral ABME, we have 1, 2, 3 rectangles, and therefore this fourth rectangle must be equal to 90 degrees in size. According to the rule, it says that the sum of the angles in any quadrilateral is equal to 360 degrees. We already done it in the first method, so we do it quickly. So in quadrilateral ABME we have 4 rectangles. Therefore we can write to quadrilateral ABME as a rectangle. We define the length of perpendicular EM as such. Again, it is the height to the base BC of the rectangle BEC. This is the version for height. The opposite sides of a rectangle are equal to each other. So in the upper small rectangle ABME, side AB must be equal to the opposite side EM. But AB is 3, therefore the opposite side EM must be also equal to 4 units in itself. EM equals to H and H equals to 3. The height to the base of the green triangle BEC equals to 3 units in its length. H equals to 3. In the next step, we'll focus on this upper right triangle BAE. This is the upper right triangle BAE. And we'll define this angle AEB as theta. So angle AEB equals to theta according to our definition. So in this right triangle AB, tangent theta equals to AB over AE. So it is now in the right triangle AB, upper right triangle AB. Tangent theta equals to AB over AE. Because again, this right triangle AEB, tangent theta equals to AB over AE. This is equation 1. So tangent theta equals to AB is 3 over AE. A is 1. So to the tangent theta equals to 3 over 1, that is 3. So according to equation 1, we should find out that tangent theta equals to 3. Then again, we should find out that according to equation 1, tangent theta equals to 3. We have the trigonometric identity that says that tangent 45 degrees plus theta equals to 1 plus tangent theta over 1 minus tangent theta. We define this trigonometric identity as equation 2. We already found out that tangent theta equals to 3, so we can substitute tangent theta in this equation 2 by 3. We'll do it now and get that according to equation 2, tangent 45 degrees plus theta equals to 1 plus tangent theta. And tangent theta is 3 over 1 minus tangent theta. Tangent theta is 3. So in total, we found out that tangent 45 degrees plus theta equals to 1 plus 3, that is 4, over 1 minus 3, that is minus 2. So in total, tangent 45 degrees plus theta equals to 4 over minus 2, that is minus 2. So tangent 45 degrees plus theta equals to minus 2. Coming to equation 2, tangent 45 degrees plus theta equals to minus 2. This is according to equation 2. Well, according to equation 1, we already found out that tangent theta equals to 3. This is side AD of rectangle ABCD. AD is the side of a rectangle, it is absolutely a straight line. So if you focus on the right side of the straight line AD at point E, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles from one side of a straight line is equal to 180 degrees. So if you focus on the right side of the straight line AD at point E, the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the right side of the straight line AD at point E? This is angle theta. This is angle theta. Plus this angle that is 45 degrees inside. Plus this missing angle, that is actually angle DEC. In total, the sum of those angles must be equal to 180 degrees according to all 3. Again, in total, the sum of those angles must be equal to 180 degrees according to all 3. So here we subtract theta plus 45 degrees from this equation. And you get that the missing angle DEC is equal to 180 degrees minus theta plus 45 degrees. So actually, this is the missing angle DEC. This is equal to 180 degrees minus theta plus 45 degrees. In the next step, we focus on this right lower triangle, triangle EDC. This right lower triangle, triangle EDC, tangents 180 degrees minus theta plus 45 degrees equals to DC over DE. Again, tangents 180 degrees minus theta plus 45 degrees equals to DC over DE. So write it down. Repeat again, in this right triangle EDC, tangents 180 degrees minus theta plus 45 degrees equals to DC over DE. DC equals to 3 over DE, D equals to X. We found out that tangents 180 degrees minus theta plus 45 degrees equals to 3 over X. This is equation 3. So I copy the equation 3 in a new page. According to equation 3, we found out that tangents 180 degrees minus theta plus 45 degrees equals to 3 over X. Repeat again. According to equation 3, we found out that tangents 180 degrees minus theta plus 45 degrees equals to 3 over X. We have another trigonometric identity. It says that tangents 180 degrees minus theta equals to minus tangents theta. We'll use this trigonometric identity in order to find out the value of tangents 180 degrees minus theta plus 45 degrees. According to this trigonometric identity, the value of tangents 180 degrees minus theta plus 45 degrees will be equal to minus tangents theta plus 45 degrees. And again, according to this trigonometric identity, tangents 180 degrees minus theta equals to minus tangents theta. The value of tangents 180 degrees minus theta plus 45 degrees will be equal to minus tangents theta plus 45 degrees. So we can substitute tangents 180 degrees minus theta plus 45 degrees by minus tangents theta plus 45 degrees, because those two expressions are identical according to this trigonometric identity. So we do it now, we get that according to equation 3. Equation 3, we have tangents 180 degrees minus theta plus 45 degrees, but it's equal to minus tangents theta plus 45 degrees. So we substitute tangents 180 degrees minus theta plus 45 degrees by minus tangents theta plus 45 degrees. And it is equal to 3 over X. Equals to 3 over X. According to equation 2, we found out that according to equation 2, we already found out that times 45 degrees plus theta equals to minus 2. So we substitute times 45 degrees plus theta here by minus 2. This equation, equation 3. We do it now and get it very minus, so I'll copy the minus here. And according to equation 2, times 45 degrees plus theta equals to minus 2. So we substitute times 45 degrees plus theta by minus 2. And it equals to 3 over x. Minus times minus is plus, so minus 2 is plus 2. According to equation 3, if we found out that 2 equals to 3 over x. Here we will multiply this equation by x, equation 3. And you get that according to equation 3, 2x equals to 3. It's definitely allowable to multiply the equation by x because x is the length of this line segment ED, therefore it can never be equal to 0, it must be a positive number. So 2x equals to 3. Here we divide this equation by 2. You get that x equals to 3 halves. 3 halves is 1.5. So total we should find out that x, which is the length of this line segment ED, is equal to 1.5 units in its length. X equals to 1.5 units. Our task is to find out the area of this green shape. The green shape is triangle ABC. The green shape is triangle ABC, so our task is to find out the area of this green triangle, EBC. And again, because of the fact that the green shape is triangle ABC, so our task is to find out the area of the green triangle ABC. Note that the area of any triangle equals to the base of the triangle times the height over 2. We'll choose the base of this green triangle EBC as BC. The height is h because of the fact that h creates that with the base, BC. The height is h over 2. BC is x plus 1 times the height h is 3 over 2. We already found out that x equals to 1.5. Therefore x plus 1 must be equal to 1.5 plus 1, that is 2.5. So the base BC is 2.5 units. Times 3 over 2. 2.5 times 3 is 7.5 over 2. 7.5 over 2 is 3.75 square units in its size. So actually, in both methods, we found out that the area of this green shape, that is the area that we are looking for this question, is equal to 3.75 square units in size. So we finish with the first question. In the next step, I present to the second question, and we will solve the second question of this lecture. In the second question, our task is to find out the radius of this semicircle that is described by rectangle ABCD. Okay, again, our task is to find out the radius of this semicircle that is described by rectangle ABCD. So in the drawing we have rectangle ABCD. This is line 7 cubit, it is equals to 1 unit in its length. This is line 7 PD, it is equals to 2 units in its length. Inside rectangle ABCD we have this semicircle that is described by this rectangle ABCD. Side BC is tangent to this semicircle at this point, and side CD is tangent to this semicircle at this point. Again, our task is to find out the radius of this semicircle. It is described by rectangle ABCD. So first of all, ABCD is a rectangle, therefore all those four angles are right angles. In the next step, we'll define the point of tendency of tangent DC with this semicircle. This point is point T. Likewise, we define the point of tendency of tangent BC with this semicircle. This point is point L. We define the center of this semicircle. This point is point O. And finally, we define the radius of this semicircle as x. In the next step, we will join points O and T together by a straight line. Point O is the center of the semicircle, point T is the point of the semicircle itself, point T is the point of the semicircle itself, therefore OT is the radius of the semicircle that is equals to x according to our definition. The radius OT is equals to x, the radius OT is drawn to point T, that is the point of tendency of tangent DC with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius TO. If this is perpendicular to TO, it means that this angle equals to 90 degrees in its size. And this angle also equals to 90 degrees in its size according to rule 1. Likewise, we will join points O and F together by a straight line. Point L is the point of tendency of tangent BC with this semicircle. OL is of course the radius of this semicircle, that is equal to x. The radius OL is equal to x, the radius OL is drawn to point L, that is the point of tendency of tangent BC with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius ALO. If BC is perpendicular to ALO, it means that this angle equals to 90 degrees in its size, and this angle equals to 90 degrees in its size according to the same rule, rule 1. So by doing those constructions, you can derive the small lower quadrangle OLCT. Inside this lower quadrangle OLCT, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 pieces again. In total, they must be equal to 360 degrees. according to the rule that says that the sum of the areas in any quadrilateral is equal to 360 degrees. And therefore this fourth area must be equal to 90 degrees in its size. According to rule 5, any quadrilateral that is equal to 90 degrees, according to rule 5, any quadrilateral that has 4 right areas must be at least a rectangle, if not a square. So we relate to quadrilateral OLCT. It's a rectangle because it has 4 right angles. So in rectangle OLCT, the opposite sides are equal to each other. That is to say, side OT equals to the opposite side LC. But OT is x, therefore the opposite side LC must be also equal to x units in its length. Likewise, according to the same rule, in the same rectangle OLCT, side OL must be equal to the opposite side TC. But OL is x, therefore the opposite side TC must be also equal to x units in its length. So if you found out that quadrilateral OLCT is not a rectangle but a square, why? Because of the fact that all of its sides are equal to each other, its side equal to x. So now it is down. In the next step, we will do a construction, that is to say from point O, that is the center of the semicircle, we will do perpendicular on AB. Again, from point O, we will do perpendicular on side AB of rectangle ABCD. So actually, this angle equals to 90 degrees in size, and this angle also equals to 90 degrees in size according to our construction. We define the touching point of the perpendicular from point O and AB. This point is point S. By doing this construction, we can deduce the upper quadrilateral SBLO. Inside this quadrilateral SBLO, we have 1, 2, 3 rectangles. And therefore, this fourth rectangle must be equal to 90 degrees in size. According to the rule that said that the sum of the angles in any quadrilateral is equal to 360 degrees. So in quadrilateral SBLO we have 4 rectangles, and therefore we can relate to this quadrilateral SBLO as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. Again, the opposite sides of a rectangle are equal to each other. So in the upper small rectangle SBLO, the opposite sides must be equal to each other. That is to say, side OL must be equal to the opposite side SB. But OL is x, therefore the opposite side SB must be also equal to x units in its length. That is known. This is the opposite side SB. This is equal to x units in its length. What is the length of this line segment SQ? SQ in total equals to SB minus QB. So it is known SQ, the missing line segment SQ in total is equal to SB minus QB. So in total, the missing side SQ, the missing line segment SQ equals to SB. SB is x minus QB. QB is 1 according to what is given us in the question. So in total, SQ equals to x minus 1 units in its length. This is the missing side SQ. This equals to x minus 1 units in its length. In the next step, we will do another construction. That is to say, from point O, that is the center of this semicircle, we will do perpendicular on AD. Again, from point O, we will do perpendicular on side AD of rectangle ABCD. So actually, this angle equals to 90 degrees in size, and this angle also equals to 90 degrees in size according to our construction. We will define the touching point of the perpendicular from point O and AD. This point is point Z. When doing this construction, we created the upper right quadrilateral ACOZ. Inside this quadrilateral ASOZ, we have 1, 2 rectangles, and therefore this fourth rectangle must be equal to 90 degrees in size according to the sum that I already mentioned a couple of times. It says that the sum of the angles in any quadrilateral is equal to 360 degrees. So quadrilateral ASOZ is 4 right angles, and therefore we can relate to quadrilateral ASOZ as a right angle. When doing this construction, we get the lower quadrilateral OZ dt. Inside this quadrilateral OZ dt, we have 1, 2, 3 angles, and therefore this fourth angle must be equal to 90 degrees in its size. So the lower quadrilateral OZ dt is 4 angles, and therefore can relate to quadrilateral OZ dt as a rectangle. So in total, in the drawing we have 3 rectangles and 1 square. So we have the rule that says that the opposite sides of a rectangle are equal to each other. So in the lower small rectangle OZ dt, the opposite sides must be equal to each other. That is to say, side OT must be equal to the opposite side ZD. But OT is x, therefore the opposite side ZD must be also equal to x units in its length. What is the length of this missing line segment ZP? ZP equals to ZD minus PD. Again, ZP equals to ZD. ZP equals to ZD minus PD. So, write it down. The length of the missing line segment ZP is equal to ZD minus PD. In total, the missing line segment ZP equals to ZD is x minus PD. PD is 2 according to what is given as the question. So in total, the missing line segment ZP equals to x minus 2 units in its length. This is the missing line segment ZP. This is equal to x minus 2 units in its length. This is the big angle LOZ. The big angle LOZ equals to 90 degrees plus 90 degrees, that is 180 degrees. So I'll write it down. The big angle LOZ equals to 180 degrees in its size. It again. The big angle LOZ equals to 180 degrees in its size. And we know that any angle that equals to 180 degrees in its size, it is defined as a straight line. Therefore, angle LOZ is a straight line. That is to say, line segment LOZ is a straight line. If line segment LOZ is a straight line, LZ must be also a straight line. And therefore, this shape, the upper shape ABLZ, has 4 sides in total. 1, 2, 3, 4. So, write it down. The upper shape ABLZ has 4 sides. Shape ABLZ has 4 sides, and therefore it must be a quadrilateral. Shape A, B, and Z is a quadrilateral. So this is quadrilateral A, B, L, Z. That has 1, 2, 3, 4 right angles. So with the norm, the upper quadrilateral L, B, and Z has 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to quadrilateral A, B, and Z as a rectangle. Quadrilateral A, B, and Z is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the upper rectangle A, B, and Z, the opposite sides of a rectangle are parallel to each other. So in the upper rectangle A, B, and Z, side AB must be parallel to the opposite side ZL. It again. In the upper small rectangle A, B, and Z, the opposite sides are parallel to each other. That is to say, side AB is parallel to the opposite side ZL. So AB is parallel to ZL, and this is transversal QP. Transversal QP cuts those two parallels, AB and ZL, at those 2 points Q and O. And again, transversal QP cuts those two parallels at those 2 points Q and O. So actually all the requirements of rule 10 are satisfied, and therefore we can implement rule 10. Complete quickly rule 10. According to rule 10, corresponding angles between parallel lines are equal to each other. So in the drawing we have line A that is parallel to line B. The red line C is transversal. That is to say, it cuts those two parallels A and B at those 2 points. And those two angles are defined as corresponding angles, and they are located between the parallels A and B, therefore they must be equal to each other in their sizes. So if the size of this angle is 1, then the size of this angle must be also equal to 1, because they are equal to each other according to this rule, rule 10. Likewise, those two angles are also defined as corresponding angles, and they are located between the same parallels A and B, therefore they must be equal to each other in their sizes. So if you define the size of this angle as 2, then the size of this angle must be also equal to 2, because they are equal to each other according to this rule, rule 10. So according to this rule 10, corresponding angles between parallels are equal to each other. So we can definitely implement rule 10 in our drawing. In our drawing, all the requirements of rule 10 are satisfied. That is to say, AB is parallel to ZL, QP is the transversal that cuts the two parallels at those 2 points Q and O. Again, all the requirements of rule 10 are satisfied, and therefore we can implement rule 10. According to rule 10, those two angles are defined as corresponding angles, and they are located between the parallels A, B, and ZL, and therefore they must be equal to each other in their sizes. So if you define the size of this angle as alpha, then the size of this angle must be also equal to alpha, because they are equal to each other according to rule 10. This is the upper right triangle SQO. In this upper right triangle SQO, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Now this is the upper green triangle SQO. This lower right triangle OZP, this angle equals to alpha, this angle equals to 90 degrees, and therefore this angle must be equal to 90 degrees minus alpha. According to the sum, that said that the sum of the angles in any triangle is equal to 180 degrees. This is the lower right triangle ZOP. What is the definition of line segment OQ? Line segment OQ starts from point O, that is the center of this semicircle, and ends at point Q, that is the point of the semicircle itself. So this is exactly the definition of a radius. Therefore, OQ is the radius of this semicircle, is equal to x unit in its length according to our definition. Likewise, OP is also the radius of this semicircle, is equal to x according to our definition. Again, point O is the center of the semicircle, point P is the point on the semicircle itself, therefore OP is the radius of this semicircle, is equal to x according to our definition. In the next step, we will prove that those two green triangles can go into each other according to angle side angle rule. So, write it down. We have to prove that this is the green upper right triangle SQO, and we have to prove that this upper green triangle SQO can go into this right lower green triangle OZP. So why those two green triangles can go into each other? First of all, those two angles, they are both equal to alpha, and therefore they are equal to each other. So actually this is angle SQO in the right upper triangle the right upper green triangle SQO, and it is equal to this angle. This is actually angle ZOP. In the right lower green triangle ZOP. And again, we should find out that angle SQO in the right green triangle SQO equals to angle ZOP in the right green lower triangle ZOP. They are both equal to alpha, and therefore they are equal to each other. In addition, those two sides are both equal to x, and therefore they are equal to each other. They are both the area of the semicircle, they equal to x, and therefore they are equal to each other. So actually, this is side QO, this is the hypotenuse of this green triangle. So side QO of the green upper triangle SQO equals to this side, that is side OP of this green right lower triangle OZP. Okay, again we should find out that side QO of the green upper right triangle SQO equals to side OP of the green lower right triangle OZP. They are both equal to x, they are both the radii of the semicircle that is equal to x, and therefore they are equal to each other. Finally, those two angles are both equal to 90 degrees one solve, and therefore they are equal to each other. So actually this is again Q or S. In the right upper green triangle S or Q, and it is equal to this angle, this is actually angle ZPO. In the right green lower triangle ZPO. And again, we should find out that angle S or Q it is angle S or Q angle S or Q in the upper green triangle SQO equals to angle ZPO in the green right lower triangle ZPO. They are both equal to 90 degrees one solve, and therefore they are equal to each other. In conclusion, we found out that those two right green triangles can go into each other according to angle side angle rules. So already known, we found out that the upper green right triangle SQO congruent, this is the sign of congruent, to the right lower green triangle OZP according to angle side angle rule. That is to say, we actually found out that those two angles and the side that is included between those two angles, that is side OQ, and this green upper right triangle SOQ corresponding equal to those two angles, and the side that is included between those two angles, that is side OP, on this green right lower triangle ZPO. And therefore those two green right triangles can go into each other according to angle side angle rule. According to angle side angle rule, we have those two angles and the side that is included between those two angles, that is side QO, and this right green upper triangle SQO corresponding equal to those two angles, and the side that is included between those two angles, that is side OP, this green right lower triangle ZPO. Therefore those two green triangles can go into each other according to angle side angle rule. And from the fact that those two right green triangles can go into each other, we will derive that their corresponding sides must be also equal to each other in their lengths. According to the rule that says that the corresponding sides and congruent triangles are equal to each other. Those two green triangles can go into each other, therefore the corresponding angles must be equal to each other in the lengths, according to the rule that says that corresponding angles and congruent triangles are equal to each other. Side SQ of this green upper triangle SQO is the corresponding side of side ZO of the green lower triangle ZOP. Why those two sides are the corresponding sides? Because of the fact that both of them are located in front of this angle, this is 90 degrees one circle. Therefore, those two corresponding sides must be also equal to each other in their lengths. That is to say, side SQ equals to side ZO. SQ equals to ZO according to the rule. It said that corresponding sides and congruent triangles are equal to each other. But we already found out that SQ equals to x minus 1. So we can write here that SQ equals to x minus 1. And from this equation x minus 1 equals to XQ equals to ZO, we will derive that ZO must be also equal to x minus 1 units in its length. This is the side ZO of the green lower triangle ZPO. It is equals to x minus 1 units in its length. In the next step, we will implement the Pythagoras theorem of this green right lower triangle, triangle ZOP. according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here, by PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in this green right triangle ZPO, or P squared, that is the square of the hypotenuse, equals to OZ square plus ZP square. And again, in this green right triangle ZPO, according to the Pythagoras theorem, OP squared, that is the square of the hypotenuse, equals to OZ square plus ZP square. OP is x, therefore OP square is x square, and it is equals to OZ square. OZ is x minus 1, therefore OZ square is x minus 1 square plus ZP square. ZP is x minus 2, therefore ZP square is x minus 2 square. So in total, we should find out that x square equals to x minus 1 square plus x minus 2 square. Here we will open the brackets on this side of the equation, and we get that again we will open the brackets on this side of this equation, and we get that x squared equals to x minus 1 square. X minus 1 square equals to x square plus 1 square, that is 1, plus 2 times x times 1, that is minus 2x, and this equals to x minus 2 square. X minus 2 square equals to x square plus 2 square, that is 4, minus 2 times x times 2, that is minus 4x. So here we have x. We have x squared on both sides of this equation, so x squared will get cancelled. After we cancel x squared on this side of the equation, we left with nothing, that is to say 0. While on the other side of the equation, we have 1 plus 4 is 5, minus 2x minus 4x is minus 6x, and we have also x squared. So in total we should find out that x squared minus 6x plus 5 equals to 0. So this is a quadratic equation, and the general formula for a quadratic equation is as follows. Ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation. And x is the variable that we are looking for. And we will find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. Another specific quadratic equation, that is to say x squared minus 6x plus 5 equals to 0. The variable that we are looking for is x, and x is the radius of this semicircle. So, as you know, x is the radius of the semicircle. The coefficient a equals to 1, the coefficient b equals to minus 6, and the coefficient c equals to 5. The only thing that is left to do in order to find out the radius of the semicircle x is just to put this the specific data of our specific quadratic equation inside this general formula for x. In this way we find out the value of the values of x, because x might have two solutions. So we do it now, and we get that so we put the data of our specific quadratic equation inside this general formula for x, and we get that x, that is the radius of the semicircle, equals to minus b. B is minus 6, therefore minus b is minus 6, that is plus 6, plus minus square root of b squared. B is minus 6, therefore b squared is minus 6 squared, that is 36, minus 4 times a times c. So this is minus 4 times a is minus 4 times 1 is minus 4, times c is 5, so minus 4 times 5 is minus 20, over 2a. A is 1, so 2a is 2 times 1, that is 2. So in total we should found out that x, that is the radius of the semicircle, that is the radius that we're looking for in this question, equals to 6 plus minus. Inside the root we have 36 minus 20 is 16. So inside the root we left only with 16. Over 2. Okay, so in total we found out that x equals to 6 plus minus square root of 16 over 2. The square root of 16 is 4. So in total we found out that x equals to 6 plus minus, again the square root of 16 is 4 over 2. So here we have two solutions that are possible for x. Okay, again that x is the radius of the semicircle. So the first solution for x is as follows. X equals to 6 plus 4 over 2. 6 plus 4 is 10, and 10 over 2 is 5. So the first solution for x is x equals to 5. That is to say, the radius of this semicircle equals to 5 units in its length. Radius x equals to 5 units in its length. We have another solution for x. The second solution for x is as follows. X equals to 6 minus 4 over 2. 6 minus 4 is 2, and 2 over 2 is 1. So the second solution for x is 1. This is to say, the radius of this semicircle equals to 1 unit in its length. We already found out that line 7zp equals to x minus 2 units in its length. So write it down. Line 7zp is equal to x minus 2 units in its length. If x equals to 5, then zp equals to 5 minus 2, that is 3, so it is definitely possible that the length of this line 7zp is equal to 3 units. But what is happening if x equals to 1, then if x equals to 1, then ZP equals to x minus 2. X minus 2 is 1 minus 2, that is minus 1. But because of the fact that ZP is length, the length of this 9 segment, ZP is a length, it must be a positive number. But here you arrive to the conclusion that ZP is a negative number, so therefore x can never be equal to 1 due to the contradiction. ZP can never be equal to a negative number, so the second reason that x can never be equal to 1 because of the fact that again ZP equals to x minus 2 and ZP is a left, so it's a left, it must be a positive number. That is to say ZP is equals to x minus 2. What is a positive number? That is to say it must be greater than 0. So here we add 2 to this inequality and we get that x must be greater than 2. If x must be greater than 2, then x can never be equal to 1, that is less than 2. So due to the contradiction, we cancel the solution, x can never be equal to 1, and we will take into account only the second solution for x. That is to say, the radius of the semicircle equals to x is equal to 5 units in its length. Okay, again, we should find out that the radius of this semicircle x equals to 5 units in its length. So we finish with the second question. In the next step, I will summarize the lecture. I'll start with the repetition of the first question, before its two methods, and then repeat on the solution of this second question. The first question, our task is to find out the area of this ring shape. So in the drawing we have a rectangle ABCD. This is line segment AE, this is equals to 1 unit in its length. Side AB of rectangle ABCD equals to 4 units in its length. Inside this rectangle we have this ring shape. The ring shape is actually triangle EBC. Angle BEC equals to 45 degrees inside, and our task is to find out the area of this ring shape. This is actually the area of this great triangle BEC. First of all, because of the fact that ABCD is a rectangle, all those four areas are right angles. In the next step, we define line segment ED as x. We also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC. But AB equals to 3, therefore the opposite side DC must be also equal to 3 units in its length. Likewise, according to the sum rule, in the same rectangle ABCD, side AD must be equal to the opposite side BC, but AD in total is x plus 1, therefore the opposite side BC must be also equal to x plus 1 units in its length. The next step, we did a construction, that is to say from point E we drew perpendicular on BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BC. This point is point M. By doing this construction, we get the quadrilateral ABME. Inside this quadrilateral ABME, we have 1, 2, 3 right angles. 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 3 angle, in total it must be equal to 360 degrees. According to the rule, that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this 4 3 angle must be equal to 9 degrees in its size. So in quadrilateral ABME, we have 4 angles. Therefore, can relate to this quadrilateral ABME is right angle. But we also know that the opposite sides of right angle are equal to each other. So in right angle ABME, side AB must be equal to the opposite side DM. But AB is 3, therefore the opposite side EM must be also equal to 3 units in its length. We define the length of EM as h. It's actually the height to the base BC of the triangle, the green triangle ABC. H is abbreviation for height. So EM equals to h equals to 3. Okay, so in the next step, we implemented the Pythagoras theorem on this upper right triangle BAE. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in this right triangle BAE, BE squared, that is the square of the hypotenuse, equals to BA squared plus AE squared. Repeat again, this upper right triangle BAE, according to the Pythagoras theorem, BE squared, that is the square of the hypotenuse, equals to AB squared plus AE squared. BE is the missing tangent, so limit as it is. So it is BE squared equals to AB squared. AB is 3, therefore B squared is 3 squared, that is 9, plus A squared. A is 1, therefore A squared is 1 squared, that is 1. So now we found out that BE squared equals to 9 plus 1, that is 10. BE squared equals to 10. B squared equals to 10. Here we took out of this equation and we found out that the missing hypotenuse BE is equal to the square root of 10 units in its length. BE equals to the square root of 10 units in its length. The next step, we implemented the Pythagoras theorem. This right lower triangle EDC. This right lower triangle EDC, EC squared, that is the square of the hypotenuse, equals to ED squared plus DC squared. Repeat again, the right lower triangle EDC, EC squared, that is the square of the hypotenuse, equals to ED squared plus DC squared. EC is the missing hypotenuse, so we leave it as it is. So it is EC squared equals to ED squared. ED is x, therefore ED squared is x squared plus DC squared. DC is 3, therefore DC squared is 3 squared, that is 9. So total we found out that EC squared equals to x squared plus 9. Here we took out of this equation and found out that the missing hypotenuse EC equals to the square root of x squared plus 9 units in its length. This is the hypotenuse EC, this equals to the square root of x squared plus 9 units in its length. Our task is to find out the area of this green shape. The green shape is actually the green triangle ABC. So we calculated the area of this green triangle ABC using two different methods. And then we created the equation 3 that says that the area of this green triangle ABC according to the first method of calculation must be equal to the area of this green triangle ABC according to the second method of calculation. So according to the first method of calculation, note that the area of any triangle equals to the base of the triangle times the height over 2. Choose the base of this green triangle ABC as BC, so the base is BC times the height edge over 2. So according to the first method of calculation, the area of this triangle ABC equals to the base BC times the height edge over 2. BC is x plus 1, edge is 3. Again, BC is x plus 1, edge is 3, so in total, the area of the green triangle ABC according to the first method of calculation equals to x plus 1 times 3 over 2. Okay, again, according to the first method of calculation, the area of the green triangle ABC equals to 3 times x plus 1 over 2. In the next step, we calculated the area of this green triangle ABC in a different way. this is triangle ABC that could be any triangle. Side AB of this triangle ABC equals to A unit in there. Side AB equals to A unit in there. This is side AC. This is equals to B unit in there. The angle between side AB and side AC is theta. In this triangle ABC that could be any triangle, the area of this triangle ABC equals to A times B times 1 straight over 2. So the area of any triangle equals to the multiplication of the two sides by each other times 1 triangle between those two sides over 2. So actually use the new formula in order to find out the area of this triangle BC. You can definitely use the new formula because triangle ABC could be any triangle. So in this triangle BC, according to the formula, the area of this triangle BC must be equal to the multiplication of those two sides by each other. That is to say, it is BE times CC times sin 45 degrees over 2. So according to the second method of calculation, the area of this triangle BC equals to the multiplication of the two sides by each other. That is to say, it is EB times EC times sin 45 degrees over 2. This is according to equation 2, and according to equation 1, we have already found out that the area of the same green triangle BC equals to 3 times x plus 1 over 2. The next step, we created equation 3 that says that the area of the green triangle BC according to the first method of calculation must be equal to the area of the same green triangle BC according to the second method of calculation. According to the first method of calculation, the area of the green triangle BC equals to 3 times x plus 1 over 2. Well, and it must be equal to the area of the same green triangle ABC according to the second method of calculation. And according to the second method of calculation, the area of the green triangle ABC equals to EB times AC times 145 degrees over 2. So here we have 2 on both sides of this equation, so 2 will get cancelled. After you cancel 2, in this side of the equation, we left only with 3 times x plus 1, and this equals to EB is square root of 10 times EC is square root of x squared plus 9, and sin 45 degrees is square root of 2 over 2 divided by 2. So actually we cancelled 2 on both sides of the equation, so in this side of the equation we left with only 1 2 because sin 45 degrees equals to the square root of 2 over 2. Those 2 were cancelled. So after we should find out that 3 times x plus 1 equals to the square root of 10 times the square root of 2 is the square root of 20 times x squared plus 9 divided by 2. And so we have 3 times x plus 1 equals to, we substitute 20 by 4 times 5, so inside the root we have 4 times 5 times x squared plus 9 over 2. Square root of 4 is 2, so we took 4 out of the root, so inside the root we left only with 5. So in total we found out that 3 times x plus 1 equals to, again, square root of 4 is 2, so inside the root we left only with 5 times x squared plus 9 over 2. We have 2 in the numerator, 2 in the denominator, so 2 will get cancelled. After cancel 2, we should find out that 3 times x plus 1 equals to the square root of 5 times the square root of x squared plus 9. Okay, again, after we cancel 2, we found out actually that 3 times x plus 1 equals to the square root of 5 times the square root of x squared plus 9. Here we squared both sides of this equation, equation 3, and found out that according to equation 3, 3 squared is 9, and we have to square also x plus 1, so it is x plus 1 squared, and it equals to the square root of 5 squared. The square root of 5 squared is 5 times the square root of x squared plus 9 squared. This is x squared plus 9. Why? Because of the fact that the square cancels the root, and we left only x squared plus 9. So in total we found out that according to equation 3, 9 times x plus 1 squared equals to 5 times x squared plus 9. So it is 9 times x plus 1 squared. X plus 1 squared equals to x squared plus 1 squared, that is 1, plus 2 times x times 1, that is 2x. And it is equals to 5 times x squared is 5x squared, and 5 times 9 is 45. So in total we found out that 9 times x squared plus 1 plus 2x equals to 5x squared plus 45. Here we open the brackets on this side of this equation, equation 3, and found out that 9 times x squared is 9x squared, plus 9 times 1 is 9, plus 9 times 2x is 18x, and it equals to 5x squared plus 45. Here we subtract 5x squared from this equation, equation 3, and find out that 9x squared minus 5x squared is 4x squared, plus 9 plus 18x equals to 45. Here we subtract the 45 from this equation, equation 3, and find out that according to this equation, equation 3, 4x squared and plus 18x, and 9 minus 45 is minus 36 equals to 0. 45 minus 45 is 0. So here we divided this equation 3 by 4, and finally found out that 4x squared over 4 is x squared, 18x over 4 is 4.5x, and minus 46 over 4 is minus 9 equals to 0 over 4 is 0. So in total we found out that x squared plus 4.5x minus 9 equals to 0. So this is the quadratic equation, and the general formula for quadratic equation is as follows. Ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we will find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2. In our specific quadratic equation, that is to say, x squared plus 4.5x minus 9 equals to 0. The variable that we are looking for is x. X is the length of this 97 AD. The coefficient a equals to 1, the coefficient b equals to 4.5, and the coefficient c equals to minus 9. The only thing that is left to do in order to find out the length of 97 AD is equals to x is just to put the data of our specific quadratic equation inside this general formula for x. In this way we find out the value of the values of x, because x might have two solutions. So we did it, and actually found out that x equals to minus b. B is 4.5, therefore minus b is minus 4.5, plus minus b squared. B is 4.5, and therefore b squared is 4.5 squared, that is 20.25. Minus 4 times a times c. So it is minus 4 times a. A is 1, so minus 4 times 1 is minus 4 times c. C is minus 9, so minus 4 times minus 9 is plus 36. So in total inside the root we have 20.25 plus 36 divided by 2a. A is 1, so 2a is 2 times 1, that is 2. So 20.25 plus 36 equals to 56.25. So in total we should find out that x equals to minus 4.5 plus minus square root of 56 over 2. The square root of 56.20, the square root of 56.25 is 7.5. So in total we should find out that x equals to minus 4.5 plus minus 7.5 over 2. Here we have two solutions that are possible for x. The first solution for x is as follows. X equals to minus 4.5 plus 7, minus 4.5 minus 4.5 minus 7.5 over 2. Minus 4.5 minus 7.5 is minus 12, and minus 12 over 2 is minus 6. Because of the fact that x is the length of this 97 ED, s as a length, it must be a positive number, therefore it can never be equal to minus 6, that is a negative number. So the first solution for x is incorrect solution. So we'll take into account only the second solution for x. The second solution for x is as follows. X equals to minus 4.5 plus 7.5 over 2. Minus 4.5 plus 7.5 equals to 3. 3 over 2 is 1.5. So in total, we found out that the length of this last element ED is equal to x is equal to 1.5 units. Our test is to find out the area of this green shape. The green shape is actually the green triangle ABC. So our test is to find out the area of this green triangle ABC. Read again. The area of the green shape is actually the area of the green triangle ABC. The area of the triangle equals to the base of the triangle times the height over 2. Choose the base of this triangle ABC as BC. The height is h over 2. So the area of the green triangle ABC equals to the base BC times the height h over 2. We already found out that BC, the base BC equals to x plus 1 and h equals to 3. And again, BC equals to x plus 1 and AD equals to 3 divided by 2. X is 1.5, so x plus 1 is 1.5 plus 1, that is 2.5 times 3 over 2. 2.5 times 3 is 7.5, and 7.5 over 2 is 4.75 square in size. So according to the first method, we actually found out that the area of this great shape, that is the area that we are looking for in this question, is equal to 3.75 square in size. So we finish with the first method. In the next step, I'll fit in the solution of the second method. ABCD is a rectangle, therefore all those four angles are right angles. We define the length of AD is x. We know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AD equals to the opposite side BC, but AD is x plus 1, therefore the opposite side BC must be also equal to x plus 1 units in its length. Likewise, according to the same rule, in the same rectangle ABCD, side AB must be equal to the opposite side DC, but AB is 3, therefore the opposite side DC must be also equal to 4 units in its length. The next step, we did the construction, that is to say from point E we draw perpendicular on BC. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point E and BC. This point is point M. By doing this construction, we added the upper quadrilateral AB and ME. Inside this upper quadrilateral AB and ME, we have 1, 2 triangles. The sum of triangles is 270 degrees, so 270 degrees plus the size of this fourth angle, in total must be equal to 360 degrees. According to the rule that said that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth angle must be equal to 90 degrees in its side. So inside quadrilateral AB and ME we have 4 angles, and therefore we can relate to this quadrilateral AB and ME is a rectangle. But you also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle AB and ME, side AB must be equal to the opposite side EM. But AB is 3, therefore the opposite side EM must be equal to 3 units in its length. We define the length of the perpendicular EM is h, so EM equals to h equals to 3. H is the height of the base BC of the great triangle BEC. That's what is information for the height, for height. In the next step, we focus on this upper right triangle AEB. We define this angle AEB is theta. So in this upper right triangle AEB, tan theta equals to AB over AE. And again, this right triangle AB, it is very easy to see that tan theta equals to AB over AE. AB is 3, AE is 1. So in total, tan theta equals to 3 over 1, that is 3. Again, according to equation 1, tan theta equals to 3. We have the trigonometric identity that said that tangent theta plus 45 degrees or tangent 45 degrees plus theta equals to 1 plus tangent theta or 1 minus tangent theta. So we define this trigonometric identity, it's equation 2. We already found out that tangent theta equals to 3, so we can solve the tangent theta in this equation 2 by 3. We did it, and we found out that according to equation 2, tangent 45 degrees plus theta equals to 1 plus tangent theta is 3. And over 1 minus tangent theta, again tangent theta is 3. So in total, we should find out that tangent 45 degrees plus theta according to equation 2 equals to 1 plus 3, that is 4, over 1 minus 3, that is minus 2. 4 over minus 2 equals to minus 2. So in total, we should find out that according to equation 2, tangent 45 degrees plus theta equals to minus 2. Because again, according to equation 2, we should find out that tangent 45 degrees plus theta equals to minus 2. While according to equation 1, we actually found out that tangent theta equals to 3. In the next step, we focus on this. AD is one side of rectangle ABCD, therefore it is absolutely a straight line. So if you focus on the right side of the straight line AD at point D, here the sum of the angles must be equal to 180 degrees according to 3. Rule 3 said that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the right side of the straight line AD at point E? We have this angle theta, plus this angle is equal to 45 degrees inside, plus this missing angle DEC. In total, the sum of those three angles must be equal to 180 degrees according to all three. So repeat again, if you found out that if you focus on the right side of the straight line AD at point D, we know that the sum of the angles at the right side of the straight line at the right side of the straight line AD at point D must be equal to 180 degrees. So which angles we have at the right side of the straight line AD at point D? We have angle theta plus 45 degrees plus the missing angle DEC, the third missing angle DEC. In total must be equal to 180 degrees according to all three. Here we subtract theta plus 45 degrees from this equation. If I found out that the missing angle DEC equals to 180 degrees minus theta plus 45 degrees. So this is the missing angle DEC is equals to 180 degrees minus theta plus 45 degrees. The next step we focus on this right lower triangle, triangle EDC. In this right lower triangle EDC, triangle is 180 degrees minus theta plus 45 degrees equals to DC over ED. And again, this right lower triangle EDC, triangle is 180 degrees minus theta plus 45 degrees equals to DC over DE. DC is 3, DE is X. So total triangle is 180 degrees minus theta plus 45 degrees equals to 3 over X. Repeat again. According to equation 3, triangle is 180 degrees minus theta plus 45 degrees equals to 3 over X. We have another trigonometric identity that says that triangle is 180 degrees minus theta equals to minus triangle theta. So according to this trigonometric identity, triangle is 180 degrees minus theta plus 45 degrees equals to minus triangle theta plus 45 degrees. Again, the value of this expression triangle is 180 degrees minus theta plus 45 degrees equals to minus triangle theta plus 45 degrees according to this trigonometric identity. Therefore, we can substitute triangle is 180 degrees minus theta plus 45 degrees by minus triangle theta plus 45 degrees because those two expressions are identical according to this trigonometric identity. So we substitute triangle is 180 degrees minus triangle theta plus 45 degrees by minus triangle theta plus 45 degrees, and it equals to 3 over X. So copy it here. So according to equation 3, I have found out that minus triangle theta plus 45 degrees equals to 3 over X. But according to equation 2, we already found out that triangle theta plus 45 degrees equals to minus 2. Well, this is equation 2. According to equation 2, we already found out that triangle 45 degrees plus theta equals to minus 2. So we can substitute triangle theta plus 45 degrees by minus 2. We have here minus, so I copy the minus here, and we have triangle theta plus 45 degrees equals to minus 2 according to equation 2. So in total we have this out of this equation 3, we have minus 2 equals to 3 over X. Minus times minus is plus, so minus 2 is plus 2. So 2 equals to 3 over X. Here we divided this equation, we multiplied this equation by X and finally found out that 2X equals to 3. Here we divided this equation by 2 and finally found out that X equals to 3 over 2, that is 1.5. So X equals to 1.5 units in this length. The graph of this line it is equals to X is 1.5 units. Our test is to find out the area of this grain shape. The grain shape is actually the grain triangle ABC. Again, our test is to find out the area of the grain shape, and the area of the grain shape is actually the area of the grain triangle BC. We know that the area of the triangle equals to the base of the triangle times the height of the base over 2. Therefore, the area of this grain triangle ABC must be equal to the base BC times the height edge over 2. The area of our grain triangle BC must be equal to the base BC times the height edge over 2. BC is x plus 1, edge is 3. BC is x plus 1, edge is 3. So in total, the area of the grain shape equals to x plus 1 times 3 over 2. x is 1.5, therefore x plus 1 is 1.5 plus 1, that is 2.5. So the base BC is 2.5 times the edge that is 3 over 2. 2.5 times 3 is 7.5, and 7.5 over 2 is 3.75 squares in size. So actually in both methods, we actually found out that the area of this region, that is the area that we are looking for this question, is equal to 3.75 squares in size. We finish with the first question. In the next step, we repeat on the solution of the second question. The second question, our task is to find out the radius of this semicircle that is described by rectangle ABCD. So in the drawing we have rectangle ABCD. This is line segment QB, this is equal to 1 unit in its length. This is line segment PD, this is equal to 2 units in its length. And our task is to find out the radius of this semicircle that is described by rectangle ABCD. First of all, ABCD is a rectangle, therefore all those four areas are right angles. We define the point of tendency of tangent DC with this semicircle, this point is point T. Likewise, we define the point of tendency of tangent BC with this semicircle, this point is point L. We define the radius of this semicircle as X, and we define the center of this semicircle, this point is point O. In the next step, we join points O and T together by straight line. Point O is the center of the semicircle, point T is the point of the semicircle itself, therefore OT is the radius of this semicircle, is equals to X. The radius of T is equal to X, the radius of T is drawn to point T, that is the point of tendency of tangent DC with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then DC will be perpendicular to the radius TO. If DC is perpendicular to TO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and T together, O and L together by straight line. OL is of course the radius of this semicircle, that is equals to X. The radius of L is equals to X, the radius of L is drawn to point L, that is the point of tendency of tangent BC with this semicircle. Whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius LO. If BC is perpendicular to LO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. By doing those construction, we already did the small quadrilateral, the small lower quadrilateral OLCT. Inside this lower quadrilateral OLCT, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth angle, total must be equal to 360 degrees according to the rule that said that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth angle must be equal to 90 degrees in size. So inside quadrilateral OLCT, we have 4 right angles, and therefore according to rule 5, any quadrilateral that has 4 right angles must be this rectangle in front and square. So we relate to quadrilateral OLCT is a rectangle because it has 4 right angles. But we also know that the opposite sides of rectangle are equal to each other. So in rectangle OLCT, side OL must be equal to the opposite side CT. But OL is X, therefore the opposite side CT must be also equal to X units in its length. Likewise, according to the sum rule, in the sum rectangle OLCT, side OT must be equal to the opposite side LC, but OT is X, therefore the opposite side LC must be also equal to X units in its length. So in conclusion, we found out that quadrilateral OLCT is not a rectangle, but a square. Why? Because all of its sides are equal to each other, its side equals to X. In the next step, we did the construction, that is to say from point O, we go perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the tangent point of the perpendicular from point O and AB. This point is point S. By doing this construction, we added the upper quadrilateral SBLO. Inside this quadrilateral SBLO, we have 1, 2, 3 angles, and therefore this fourth angle must be equal to 90 degrees inside according to the rule. that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, in quadrilateral OSBL, we have 4 angles, and therefore can relate to quadrilateral OSBLO is a rectangle. But we also know that the opposite sides of rectangle are equal to each other. So in the upper small rectangle SBLO, side OL must be equal to the opposite side SB, but OL is x, therefore the opposite side SB must also equal to x units in its length. What is the length of this line segment SQ? SQ equals to SB minus QB. Again, SQ equals to SB minus QB. So SQ equals to SB, that is x, minus QB, that is 1. So in total, SQ equals to x minus 1 units in its length. In the next step, we did another construction, that is to say from point O, we drew perpendicular on AD. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AD. This point is point Z. By doing this construction, we did the upper quadrilateral AES OZ. Inside this upper quadrilateral AES OZ, we have 1, 2, 3 rectangles, and therefore this fourth rectangle must be equal to 90 degrees inside. So in quadrilateral AES OZ, we have 4 rectangles, and therefore can relate to quadrilateral OSOZ as a rectangle. By doing this construction, we added the lower quadrilateral ZOTZ, ZOTD. Inside this lower quadrilateral ZOTD, we have 1, 2, 3 rectangles, and therefore this fourth rectangle must be equal to 90 degrees inside. According to the sum rule, that said that the sum of the angles in any quadrilateral is equal to 360 degrees. So in quadrilateral OZDT, we have 4 rectangles, therefore can relate to quadrilateral OZDT is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in the lower small rectangle OZDT, side OT must be equal to the opposite side ZD. But OT is x, therefore the opposite side ZD must be also equal to x units in its length. What is the length of this short line ZP? ZP equals to ZD minus PD. Again, ZP equals to ZD minus PD. ZP equals to ZD minus PD. So ZP equals to ZD, that is x, minus PD, that is 2, according to what is given in the question. So in total, the missing line ZP equals to x minus 2 units in its length. This is the big angle ZOL. This is equal to 90 degrees plus 10 degrees. It is 180 degrees. And again, the big angle LOZ. The big angle LOZ equals to 180 degrees in its size. And we know that any angle that is equals to 180 degrees in its size, it is defined as a straight line. Therefore, line segment LOZ is a straight line. Line segment LOZ is a straight line. So if line segment LOZ is a straight line, it means that LZ is also a straight line. Again, LZ is a straight line. And therefore, this shape, the upper shape ABLZ, is 4 sides in total. 1, 2, 3, 4. The upper shape ABLZ is 4 sides, and therefore shape ABLZ is a quadrilateral. So in this quadrilateral ABLZ, we have 1, 2, 3, 4 right angles. In quadrilateral ABLZ, we have 4 right angles, and therefore quadrilateral ABLZ is a rectangle according to Rule 5 that says that any quadrilateral that has 4 right angles must be this rectangle if not a square. So in the upper small rectangle ABLZ, the opposite sides are parallel to each other. This is to say side AB is parallel to the opposite side ZL. AB is parallel to ZL. So AB is parallel to ZL, and we also have transversal QP that cuts those 2 parallels and those 2 points, Q and O. So all the requirements of Rule 10 are satisfied, and therefore we can implement Rule 10. So I repeat quickly on Rule 10. According to Rule 10, corresponding angles between parallel lines are equal to each other. In the drawing, we have line A that is parallel to line B. The red line C is transversal. This is to say it cuts those 2 parallel lines and those 2 points. Those 2 angles are both defined as corresponding angles and are located between the parallel lines A and B. Therefore, they must be equal to each other at their sizes. So, if the size of this angle is 1, then the size of this angle must be equal to 1 because they are equal to each other. Likewise, those two angles are also defined as corresponding angles and are located between the same parallels A and B. Therefore, they must be equal to each other in their sizes. So if the size of this angle is 2, then the size of this angle must be also equal to 2, because they are equal to each other according to this rule, rule 10. So according to rule 10, corresponding angles between parallels are equal to each other. So you can definitely implement rule 10, so I mentioned before, in our drawing. Okay, again, AB is parallel to ZL. Transversal QP cuts those two parallels at points Q and O. So all the requirements of rule 10 are satisfied, and therefore we can implement rule 10. According to rule 10, those two corresponding angles that are located between the parallels AB and ZL must be equal to each other in their sizes. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha, because they are equal to each other according to rule 10. So in the upper right triangle S or Q, this angle equals to alpha, this angle equals to 9 degrees, and therefore this angle must be equal to 9 degrees minus alpha. 1 equals 9 degrees minus alpha plus alpha is 90 degrees, 90 degrees plus 90 degrees, it equals to 180 degrees, that is the sum of the angles in a triangle. Likewise, the lower right triangle OZP, this angle equals to alpha, this angle equals to 90 degrees, and therefore this angle must be equal to 90 degrees minus alpha, according to the sum of that said the sum of the angles in a triangle is equal to 180 degrees. What is the definition of line segment OQ? Line segment OQ starts from point O, that is the center of the semicircle, and then to point Q, that is the point of the semicircle itself. Therefore, OQ is the radius of the semicircle, that is equal to x. Likewise, line segment OP starts from point O, that is the center of the semicircle, and then to point P, that is the point of the semicircle itself. Therefore, OP is also the radius of this semicircle, that is equal to x. So in the next step, we prove that those two right triangles can go into each other according to side angle rule. So why those two right triangles can go into each other? First of all, those two angles are both equal to alpha, and therefore they are equal to each other. In addition, those two sides are both equal to x, and therefore they are equal to each other. Finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So we can find out that those two right triangles can go into each other according to angle side angle rule. That is to say, those two angles and the side that is included between those two angles, that is side QO, on this upper right triangle SQO corresponding equal to those two angles, and the side that is included between those two angles is the side OP, this lower triangle OZP. Therefore, those two right triangles can go into each other according to angle side angle rule. We have those two angles and the side that is included between those two angles is the side QO, this upper right triangle SQO corresponding equal to those two angles, and the side that is included between those two angles that is side QO, this right lower triangle ZOP. Therefore, those two right triangles can go into each other according to angle side angle rule. So again, we found out that the upper right triangle SQO can go to the lower right triangle OZP according to angle side angle rule. And from the fact that those two right triangles can go into each other, we will derive that their corresponding angles must be also equal to their corresponding sides must be also equal to each other, according to the rule that corresponding sides and congruent triangles are equal to each other. The two corresponding sides are SQ and ZO. So SQ equals to ZO. SQ equals to ZO, according to the rule that the corresponding sides and congruent triangles are equal to each other. But we already found out that SQ equals to x minus 1, so we can write here that SQ equals to x minus 1, and from this equation x minus 1 equals to SQ equals to ZO, we will write that OZ also equals to x minus 1 units in its length. This is line segment OZ equals to x minus 1 units in its length. We already found out that ZP equals to x minus 2. Again, ZP equals to ZD, that is x, minus PD, that is 2. So in total, ZP equals to x minus 2 units in its length. Therefore, PO of the grain triangle POZ equals to x. So in the next step, we implemented the Pythagoras theorem on this grain triangle ZOP. According to the Pythagoras theorem, OP squared, that is the square of the hypotenuse, equals to OZ squared plus ZP squared. Repeat again. In the lower right hand triangle ZOP, according to the Pythagoras theorem, OP squared, that is the square of the hypotenuse, equals to OZ squared plus ZP squared. The hypotenuse OP is x, therefore OP squared is x squared, and it equals to ZO squared. ZO is x minus 1, therefore ZO squared is x minus 1 squared, plus ZP squared. ZP is x minus 2, so ZP squared is x minus 2 squared. So in total, we actually found out that x squared equals to x minus 1 squared, plus x minus 2 squared. Open the brackets on this side of this equation. And finally found out that x squared equals to x minus 1 squared. X minus 1 squared equals to x squared plus 1 squared, that is 1, plus minus 2 times x times 1, that is minus 2x, plus x minus 2 squared. X minus 2 squared equals to x squared plus 2 squared, that is 4, minus 2 times x times 2, that is minus 2 times x times 2 is minus 4x. And so we should now know that after open the brackets, that x squared equals to x squared plus 1 minus 2x plus x squared plus 4 minus 4x. Here we have x squared on both sides of this equation, so x squared will get cancelled. After we cancel x squared, in this side of the equation we left with nothing, that is to say 0, while on the other side of the equation we have 1 plus 4 is 5, minus 2x minus 4x is minus 6x, plus x squared. So in total we should find out that x squared minus 6x plus 5 equals to 0. So this is a quadratic equation, and the general formula for a quadratic equation is as follows. Ax squared plus bx plus c equals to 0. This general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. Now a specific quadratic equation, that is to say x squared minus 6x plus 5 equals to 0. The variable that we are looking for is x, and x is the radius of this semicircle. We have to find out the radius of this semicircle, that is x. The coefficient a equals to 1, the coefficient b equals to minus 6, and the coefficient c equals to 5. The only thing that we have to do is to put the data of our specific quadratic equation inside this general formula for x. This way we find out the value of the values of x. Because x might have two solutions. And then again x is the radius of this semicircle. So we have to put the data of our specific quadratic equation inside this general formula for x, and this way we find out the value of the values of x, that is the radius of the semicircle. So if we did it, we should find out that x equals to minus b. B is 6, therefore b is minus 6, therefore minus b is minus 6, that is plus 6, plus minus square root of b squared. B is minus 6, so b squared is minus 6 squared, that is 36, minus 4 times a times c. So a is 1, so minus 4 times a is minus 4, times c is 5, so minus 4 times 5 is minus 20. So in total inside the root we have 36 minus 20 over 2a. So a is 1, so 2a is 2 times 1, that is 2. 36 minus 20 is 16, so inside the root we left only with 16. So in total we should find out that x equals to 6 plus minus 16 over 2. The square root of 16 is 4, so in total we should find out that x equals to 6 plus minus 4 over 2. So here we have two solutions that are possible for x. The first solution for x is as follows. X equals to 6 plus 4 over 2. 6 plus 4 is 10, and 10 over 2 is 5. So the first solution for x is that x, that is the radius of this semicircle, equals to 5 units in its length. We have another solution for x. The second solution for x is as follows. X equals to 6 minus 4 over 2. 6 minus 4 is 2, and 2 over 2 is 1. So if we found out that the radius of this semicircle, x equals to 1 unit in its length. But x can never be equal to 1. Why x can never be equal to 1? Because of the fact that we only found out that the length of this line ZP equals to x minus 2. Again, the length of line ZP equals to x minus 2. And if x equals to 1, then the length of line ZP equals to 1 minus 2, that is minus 1. The length of line segment can never be equal to minus 1, so due to the contradiction, we cancel the solution that x equals to 1. X can never be equal to 1. Another reason that x can never be equal to 1, again, because of the fact that zp equals to x minus 2, so zp is a length. Zp is a length, it must be a positive number. What is a positive number? That is to say it must be greater than 0. Again, zp is equals to x minus 2 must be greater than 0. That is to say it must be greater, it is a positive number, so it must be greater than 0. So we added 2 to this inequality, and so x is greater than 2. If x is greater than 2, then x can never be equal to 1 that is less than 2. So we have two different reasons that x can never be equal to 1. So we cancel the solution that x equals to 1, and we took into account on the first solution for x. This is actually the radius of this semicircle x equals to 5 units in its length. Okay, thank you very much.